All right, Physics C, we're going to be going over some information about drag. I'll have this video and then one other one for you to watch. So we'll start off on page 20 with the standards, and then we'll look at a few example situations. So for drag, students should understand the effect of drag forces on the motion of an object so you can find the terminal velocity of an object moving vertically under the influence of a retarding force depending on drag. The retarding force, that just means that it's slowing it down. So it's going to be in the opposite direction of velocity. And for terminal velocity, the acceleration is 0. So the force of drag is going to equal the force of gravity. Describe qualitatively with graphs the acceleration, velocity, and displacement of such a particle when it is released from rest or is projected vertically with specified initial velocity. Use Newton's second law to write a differential equation for the velocity as a function of time. Use the method of separation variables to derive the equation and derive an expression for acceleration. This last one's easy if you can do the ones above it because acceleration is just the derivative of velocity. So some things about drag. It's always going to be the opposite direction of velocity. It's in some way proportional to velocity. Most of the time, we'd say that the magnitude of drag is equal to the magnitude of kV. K is like a drag constant, and V would be the velocity. Sometimes it would be kV to some power, like it might be proportional to velocity squared or something like that. This is much more difficult mathematically to deal with, so most of the time in Physics C, it's just kV. And they might have another letter here instead of K. Like they might have I've seen a B there or something like that. If you're going to find velocity or acceleration or position as a function of time, that's going to require solving a differential equation by separating values and separating variables and integrating. So let's take a look at what some of that actually means like in practice. So we're going to go from page 20 to page 22. Now on the left side of page 22, you'll copy this down from the other video that I have. The left side of this is what the quiz will be on. You'll have 5 minutes to do that derivation, starting with a free body diagram and a sigma F equals ma, substituting, doing the separation of variables, all that stuff, 5 minutes to come up with the velocity as a function of time. We'll do the first round of that on Friday, and then you can come in outside of class if you need, but you can take that as many times as you need until you get 100% on it in 5 minutes. It's either 100 or nothing on that one. All or nothing, no curve, no partial credit, just 100% or 0%. Now on the right side of this page, I'm going to look at what happens when we have some mass sliding along and it has an initial velocity v0, no friction here to make it simpler, and the force of drag is going to be in magnitude kv squared. So you can see I'm not using just kv, I do have a squared up here in this one. If we look at the free body diagram, gravity down, normal force up, drag to the left. In the x direction, which is really the only direction that matters here, because we don't have friction, so we don't need the normal force for anything. In the x direction, sigma F equals ma, and the only force in the x direction is drag, and that's negative kv squared. I'm going to say to the right's positive and to the left's negative, so that we're moving in the positive direction. Our force of drag will be in the negative direction. And I get this equation, which is a differential equation, because I have a derivative of velocity and velocity itself in the same equation. To separate variables here, I'm going to move this v squared down to the bottom. So I get dv over v squared. All the v's on one side and everything involving t on the other side. So what's now the integral is what we would take here of both sides. The integral at time 0 to some later time t, and at time 0 our starting speed was v0, our ending speed is going to be some other velocity v. This will tell us velocity as a function of time. When you integrate this side, you're going to get negative 1 over v. That is negative v to the negative first power. If you think about that power rule, when I have negative v to the negative first power, I would take that negative v, I'd subtract 1 from the exponent, and I would also multiply by the exponent out in front. Those two negatives would cancel, and so that gives me a derivative of v to the negative second, which is what I have right here. So we integrate both sides of this. The left side should be easy because the integral of dt is just t. Then we'll evaluate this from t to 0. So you'd plug in t, and then you'd plug in 0, and you'd subtract the upper limit from the lower limit. That's just going to give you negative kt over m. On the right side, we have the upper limit minus the lower limit, but there's a double negative. That's going to cancel. And what I did here was add this one over to the left side, so it becomes positive 1 over v. And I added this over here. And that one, of course, was positive because of the double negatives. Then I just took and I wrote the right-hand side with a common denominator. So I multiplied this by m over m. I multiplied this by v naught over v naught. And that gives us our velocity as a function of time. And you can see here, as time becomes bigger and bigger and bigger, the bottom of this fraction gets smaller and smaller. And eventually, if t went to infinity, this whole thing would go to 0. So we started with v0. This is going to be some sort of like decay function here. And then it's going to asymptotically approach 0 as we go to infinity for time. The second example I wanted to look at is if we threw a ball upwards with an initial speed of v0. The force of drag here is going to be kv. This kind of stuff would be given to you in the problem. I'm telling you right now that that's what we're using for this example. Sigma f equals ma. And when we look at the free body, both drag and gravity point down. Our object is moving up, but all of our forces are down. So minus mg minus kv equals mdv dt. Again, this is a differential equation because we have a derivative velocity and velocity together in the same equation. I'm going to factor this negative k out, basically. That will make v positive and by itself, coefficient of positive 1 on v. Then I'll separate my variables. All of this stuff goes underneath this. I would divide that over, and the m would come over here. And then at this point here, you would integrate as your next step. I'm going to stop this one here. But this would be the integral from 0 to t, and then this would be the integral from v0 to v later on. I'm not going to go through and solve this one out all the way. You'll have a good example of how that works out over here on the left, where you're going to be doing this from the other video. This is what your quiz is going to be on. And that's it for this one. See you in class.